plenary section of the conference. And the first speaker is academician Sidorenko, and he will speak about superquantum components for brain-inspired neural networks, electronics, innovation for neuromorphic computing. Okay, so voice is yours.
Good morning, dear colleagues. First of all, thank you to the permanent organizer of series of this conference, Professor Sontea. He is employed, very enthusiastic. There's a pity this year he cannot be here, but his results we obviously we can see the series of such conferences. In my talk, I would like to give short overview of the problem of artificial neural networks and their implementation for the development of computer science and technology. This is the result of our 10 years activity in frame of the European project SpinTech. Our institute was coordinator, partners of our university and University of Twente. And then now this Erasmus Plus project, which is later on devoted to the resolve of this interesting problem. What I am going to speak about? First of all, motivation. Why it is necessary, interesting to deal with and develop artificial neural network. I give some successful examples of already existing such computers based on this architecture. Then I will demonstrate you the necessity to make the next step to develop superconducting neural network, why it is necessary. For this purpose, it is necessary to use new ideas, and for realization of these ideas in metal, we need to develop new technologies. Then I will give you example of superconducting-based elements which we have elaborated, tested, and which are ready for implementation. And in conclusion, I will speak about the possibility of further development of this area. So, why it is necessary? All who deal with microelectronics and computer science knows this empirical, so-called empirical Moore law, which demonstrates exponential increasing since 70 years, increasing the possibilities of computers. Each 2 years, number of transistors increased twice, and the working frequency increased, and the possibility of computers were increasing. On the right panel, you can see this is a huge progress in technology of semiconductor-based elements transistors, from 10 micrometers in 1971 up to 5 nanometers. IBM nowadays has works where up to 3 nanometers single transistor size. It is possible even smaller to do, but it is not possible because of energy consumption. Later I will demonstrate it. So all these computers including my notebook and yours notebook, follow to the so-called von Neumann architecture. John von Neumann, and genie, he developed modern quantum mechanics, but more he is known as inventor of the von Neumann architecture or von Neumann machine. This is computer which has the same memory shared for programs and for data treatment. That's why he proposed the new ideas always appear when it is necessary. At the end of the Second World War, it was necessary to calculate artillery tables. Artillery tables usually was prepared by mechanical arithmetic, and it took many weeks to calculate these tables for shooting by artillery shells. To accelerate this problem, von Neumann proposed and constructed first computer which called electronic numerical integrator and computer, ENIAC. ENIAC, and on the base, on vacuum tubes, on the right corner of the slide, you can see the original Great Britain made lamps or vacuum tubes, using 18,000 such tubes and several hundred kilometers of wires. He constructed ENIAC. Its weight was 30 tons, personal computer with 30 tons. But this architecture was so successful that it worked 10 years, up to 1955. And using this ENIAC computer was resolved problem of a nuclear bomb, because calculation and computer modeling of the processes, it was necessary to do huge amount of calculations. ENIAC has managed to do it. The second generation of computers appeared as John Barton and Shockley and Brattain invented germanium transistor. On the right corner you can see from museum this transistor, and instead of lamps which need a lot of energy, they used something like 60,000 germanium transistors, and it was constructed the second generation of von Neumann machines, or with architecture von Neumann. Filico 2000, later this company called IBM. In 1955, IBM called Filico Philadelphia Battery Company. It was only approximately 1 ton instead of 30 tons of the vacuum tubes. It was smaller and more rapid working. And the third generation appeared as from a single transistor, was made a revolutionary step in Texas Instruments prepared in 1970 the first chips consisting of 1,000 single transistors, and IBM machine, IBM 370, this is also from museum. This is the first computer of third generation constructed on the chips. And the last, till now, we have fourth generation of computers. All of us have computers constructed from cores. Cores, this is the LC, large-scale integration, more than 1 million, several million transistors. That's why this progress gives possibility to treat more rapid and more big database. So it was everything perfect, but here you can see one of 700 database center of famous Facebook. It is near Stockholm University where we worked. Why? Because electroenergy in Sweden is cheap and it is relatively cold. That's why the Facebook company save money for cooling down the computer. This is 1 hectare surface, 120 megawatt energy consumption, 9% electricity of the industrial developed country, Sweden. That's why only from this slide one can understand that the further progress is not possible using this usual architecture. The progress one cannot stop. It will be much more information which shall be saved, treated, transferred. That's why for a more powerful computer, it is not possible just to extend this database center and energy consumption will increase, and it is not possible. That's why it was a natural appeared idea to go to another architecture, which will be 5th generation of computer. The hint gives us nature. Our personal computer, which each of us has, the brain, energy consumption is only 20 watts. It's the most difficult problems which engineer or scientist is resolving. Our brain energy consumption not more than 20 watts. You can compare with 120 megawatts of database center based on usual fundamental architecture. Our brain has another architecture, the so-called neural network. There's 100 million synapses. Neurons are connected with 10 in power 15 synapses. Neuron, this is analog of transistor, this non-linear switching element. Synapse is linear element which his aim, his duty is to connect neurons and to change the weight of neurons, to change from 0 to 1 strength of connection of neurons. That's why it's necessary to construct artificial neurons and artificial synapses and to construct the artificial neural network, the architecture similar to brain. It was successfully done. The same famous IBM company, and in 2014 it appeared on the market the first processor which called IBM Tronciu, which was constructed from artificial neurons on the top right corner and artificial synapse bottom right corner. Both of these elements were constructed from traditional SMOS transistor, metal oxide usual transistor and usual semiconductor technology. And it needs something like 30 transistors to construct such elements. That's why here one can see the neural processors, IBM Tronciu, and here one can see several generations. In 2018, not all, 2022, it was Spinnaker, also computer with brain-like architecture, artificial neural network. It does work, it demonstrates very, very high possibility, for example, for recognition of images, to recognition in people in the crowd, or to drive out. Nowadays it is usual picture when you can see the metro train which is going without driver. And such tasks INN successfully can operate, but even database center, the same power like database center from Facebook. Instead of 120 megawatts, only 1 megawatt. 2 orders of magnitude less energy consumption, but it is still much, much more than our brain. I remind you that only 20 watts. That's why it shall be done next steps. First of all, it was demonstrated possibility to construct this new architecture, brain-like architecture, but for further energy saving, energy consumption, to reduction energy consumption, one shall invent another, to use another ideas. A quite natural idea to use, instead of semiconductor transistor, which have dissipation because they have resistivity, to use superconducting elements, and this superconducting solution shall be used to change these semiconductor elements. And this idea is not new. First, it was in 1955 proposed by Alan Brook. He proposed so-called creatron. It is a very simple device, tantal wire and small solenoid which generate magnetic field. Superconducting state of tantal wire can be suppressed by external magnetic field. And he demonstrates it is much smaller than vacuum tube and than transistor. This small thing on the hand of Alan Brook demonstrates this creatron. And he constructed even logic circuit which uses this element. But the disadvantage is magnetic field shall be too high. It was the question, is it possible to use superconductor elements but operating with magnetic fields much less, which otherwise it would not be reasonable? The answer is yes, but for this purpose one shall use new ideas. New ideas, it is to use non-conventional superconductivity, so-called for the Lapin-Chenikov state, this is coexistence superconductivity and ferromagnetism, or triplet Cooper pairing, and the loft state, it is coexistence superconductivity in ferromagnet, in superconducting layer, and the oscillating behavior of critical temperature in ferromagnet layer due to this phenomena. And on the base of this phenomena, theoretician Leonard Takerov proposed a so-called spin switch or spin valve consisting of 2 ferromagnet layers and in between superconducting layer. Changing magnetization of one of the layers, it looks like changing of thickness of this ferromagnet layer. That's why the ferromagnet layer serves like Fabry-Pérot resonator for pairing function of Cooper pairs. Superconductivity appears due to so-called Cooper pairing. 2 electrons with anti-parallel spins together they construct the quasi-particle with zero spin, and particles with zero spin, you know, it is bosons. All bosons have the same energy level, and they cannot scatter all the impurities. That's why the resistivity is exactly zero, because Cooper pair cannot scatter all the impurities. And for Cooper pair wave function, thermal flare serves like Fabric resonator, and there it will be maximum or minimum of critical temperature depending on the thickness of thermal layer. That's why if we effectively change thickness of thermal layer, changing the magnetization of our node, then we can switch from superconducting to non-superconducting state like on the right panel. And if we have elaborated technology, prepared such structures and demonstrated it does work. But the operating field for changing the magnetization is still several hundred of hertz. That's why this element can work like artificial neuron, but we need even less magnetic field for operating. And for this purpose, it can be used another idea, so-called triplet superconductivity. If the magnetization is not change opposite, just inclined, for this purpose, it is necessary only a few hertz. Then critical temperature can change like in the theoretical curve on the right panel. And we have in our laboratory here in Tiginyanu elaborated such technology which was patented, and it was described in the Springer book, Functional Structures and Metamaterials for Superconducting Spectromics. And this is the real structure for triplet spin well. And this is the characteristics on the left panel is theoretical behavior, how it should look like critical temperature dependent on the mutual magnetization of two layers in triplet region. On the right hand, one can see that it is really absolute minimum by non-linear magnetization of two layers. And here one can see the switching characteristics of such element. And the base element which was prepared using such materials. This is the Johnson junction with a weak link between two superconducting layers constructed from artificial magnet. And you can see that blue and red curves demonstrate critical temperature of this element depending on the mutual magnetization. This characteristic of such element, and on the TEM picture, you can see how it looks like this small Johnson junction, which can serve like a base of neuron. Here is constructed a sigma neuron. This is sigma-like characteristic, or a spike neuron or Gauss neuron with two such junctions. The spike neuron, it is absolute analog of our neuron. In our brain, we have spike neurons. This excitation of neuron with pulses goes from one neuron to another. That's why, okay, two more slides and finish. That's why using two such Johnson junctions, we can construct the spike neuron, which can serve like artificial analog of natural brain neuron. Another base element, synapse, can be constructed from artificial magnetic material, layer structured from which is illustrated here. Superconductor has one important parameter, so-called kinetic inductance. Inductivity, it has each conductor, so-called kinetic conductivity. But if we have superconductor where there are Cooper pairs, kinetic energy deal with movement of Cooper pairs, give additional term to inductance, the kinetic inductance. Kinetic because of motion of Cooper pairs. Above critical temperature, kinetic index is 0. Below critical temperature, it appears, and we can use in this element changing magnetization of ferrite layer. We can change kinetic inductance of such structure. On the right panel, you can see the red dot curve. This is by anti-parallel magnetization of such metamaterial. Blue curve by parallel magnetization. That's why changing magnetization of such structure, we can change impedance of such element. And here one can see the circuit consisting of artificial neuron based on those consumption and artificial synapse based on this metamaterial, and the spikes which goes through this circuit, which can be used in perceptron. On the bottom you can see the perceptron. This is the one part of neural network which can be used for recognition of the images. Using these superconducting elements, we can construct the brain-like, more precise, brain-inspired circuits, which can further be used for computer vision, such as non-conventional architecture. Thank you for your attention.
Now it's time for questions. Yeah, please.
First of all, thank you for the presentation. I think this is the future direction going forward. Having a neuromorphic chip which has built-in functionality to do lots of function, in my opinion, it's a dual-use technology. Because not only you could use it for great application, but in literature, there are documented evidence that it can be remotely controlled for not so good application. So the question is twofold. In your opinion, how could you build a protection so that remotely is not controlled? Number one. Number two, because it all depends on memory. How much memory we should have, not only to do what we want to do, but also for protection.
Thank you very much for these two questions. Practically, in your question, there are two questions. Both of them are more philosophical. I can say you that the first question is this brain-like system, when it will be developed and it will be very powerful, how we can prevent to use for terroristic purposes or other bad purposes. In this case, I can tell that each invention of people, even such simple like a knife. With knife we can cut broad, but one can kill people. With nuclear energy, one can build electric power station, or one can build atom bomb to destroy the whole civilization. This question first was raised in 19 1847 by Albert Einstein. Albert Einstein said what, I just repeat his words, that the only thing which can prevent this is a human soul. Because you cannot to sit policemen near each scientist. It is just impossible. And it was created Pagauche movement. It was conferences of Pagauche conferences where they explain the responsibility of scientists, responsibility of engineers against results of their invention. That's why the only way is education, to demonstrate what can happen. It should be repeated many times. You see that idea, first it is known only for you, for me, for specialists. The majority of population don't understand how dangerous a atom bomb or how dangerous is artificial intelligence. They think, oh, it is harmful, it is like instrument. No, it is maybe more dangerous than a atom bomb. Frankly speaking, that this science fiction which we have seen, where the struggle machines against humans, it can be, and how it is prevent the way demonstrated Einstein, that we shall speak about it, we shall repeat it, and the idea shall penetrate in the population. This is one thing. And the second question is about memory. How you see that now clouds technology make it is end-lost memory.
Yeah, I had made one statement, and I think that sort of adds to dual-use technology. To counter technology, we have to have better technology. That means you add more technology to it to prevent from its misuse.
Yes. So thank you very much for addition, co-reporter. Thank you very much.
Okay, it was really very impressive step to the future of computing what you did. My question is, you have made in fact a demonstration of principle. You have proof of existence of this neurons and synapses.
Yes,
what, in your opinion, should be the immediate next step? What are you working on? Thank you.
One step was done in Argonne National Laboratory. I was there many times. By the way, this direction, the most developed is in the United States, now in Russia and in China. These three countries have huge progress in this. First, successful examples were done in the United States. I demonstrated IBM. Since 2014, in Argonne National Laboratory, all results are closed. This is you see that the technological details shall be closed and to prevent to go in the not right hands.
Competitors.
Yes. This is one way, but another way proposed by Einstein. But for this way, the society shall be ethic enough. It is difficult. It is more difficult than to close the results. Not to publish everything. Yes. To publish, one can pictures, but not the technology.
So it's societal problem,
Yes,
problem
yes,
of society.
This is problem of society.
Technical society.
Okay, I have just one short question. The time is very important, but I saw in your pictures scale time in millisecond, picosecond, also arbitrary units. What means, why do you choose arbitrary units?
It is just for demonstration.
For demonstration.
Yes.
Okay, thank you very much. And let's give the certificate to academician.
To make photo. Just
Fail pose. Okay, it's here. We'll. Okay.
Thank you very much.
Thank you for your presentation and. Let's thank the speaker again. Thank you very much. Next, our presentation will be given by Professor Ruban.
Guests? No? Dear students and all conference participants, I would like to say gratitude to our organizers, to Technical University of Moldova, to Professor Sontea especially, Professor Tiginyanu, Sergei Railan, and the entire team who made it possible, this conference, and joined all of us together, 7 way already. And I'm really happy to show some of our results, which we are doing in the Republic of Moldova, at the Technical University of Moldova, Department of Microelectronics and Biomedical Engineering, Faculty Computers, Informatics and Microelectronics, in collaboration with Germany, with USA, France, and the entire world. We are really open for collaborations, for science, for discussions, new projects, and scientific research. So today I'll show only some of our results, recent results, mainly in collaboration with Professor Abelot from Belgium team, Professor Amelie from Germany, Rainer Radelum, and Franz Falk. And of course, entire team. So entire team means all students and PhD students involved in scientific research. Is all affiliations you have for some of these results. So now it's a big trend in developing new devices for non-invasive diagnostics and biomedical applications. So we are trying to develop such types of sensors which are to detect from breath to monitor metabolic conditions and analyze breath. Also, these types of sensors, they are really important for all other fields of research. I will mention to lots of time. Also for our motivation, since we are working many years in this field, for conventional sensors there are some questions, there are some problems like instability in harsh environments. If you want to use a breath analysis, this is again effect of humidity and a lot of different types of gases. So it's important to find some new advantages, like we explained in our works. Also, current trend of electrical cars, of increasing huge capacities of energy in small battery packs. This motivates also to develop some sensors for this. So brief analysis, food industry, and shops. Also, it's important to monitor food and so on. Also, we are studying these parts in our classes and master classes and PhDs. So trend is to develop some new hybrid materials which will combine properties of different types of materials and to make real applications for industry, for medical applications. So, for hybrid materials, this is combination of organic and non-organic compounds, and to create some new devices by using different fields, different approaches to grow these materials, and to create some hybrid materials, and a lot of different types of applications for all of this. So main point is to use the synergetic effects of these types. So in hybrid materials, people are using, like we just explained, hybrid, non-hybrid. You can see more details about these new types of materials and a series already of review papers where people try to offer new capabilities of this, to find some multifunctional applications, to use nanomedicine, to use regenerative medicine diagnostics, and so on. Of course, like you already see, and all watches and so on, and all devices are implemented nowadays, different types of sensors. So here also I use hybrid multimodal sensors to monitor people and patients and so on. Another way, especially for Republic of Moldova, is to develop new trend to do monitors not only of people, but to do monitor of growth for different plants and in agriculture. This is important not only for Moldova, but for entire planet. So this is another trend and use of these types of hybrid materials. And of course, like it is in microelectronics, everything growing up, here also the requirements and types, new types and good sensors are still increasing. Market is billions. Of course, we just saw what China, for example, only last year invested more than 500 billion on semiconductors only, and our specialties. But here also people are investing in sensors since they are required. What we can do, we are developing the complete technological steps at the Department of Microelectronics and Biomedical Engineering. That's why it's important to combine all fields, and microelectronics is mainly all technologies we possess, and biomedical is implementing and using these types. Also, we developed our technology for several years and growing different types of nanostructured materials, very simple technology ready for implementation already, and reported in a series of manuscripts. Also a new, now everybody is trying to use 3D printing. We also implemented these oxides and 3D printing, developed different types of sensors, and reported in a series of papers. So we can grow zinc oxide, copper oxide, other types of oxides, combinations after 3D printing, also creating new types of mixed oxides materials, which are investigated in Moldova and in our collaborators, universities. But of course, for unprotected, uncovered materials, it's a problem with long-term stability. So that's why we are searching for new ways to hold these materials, to obtain much better performances. So one way is, for example, to use some polymer materials. They have such ring structure, for example, silicon oxygens only, and most important is it's hydrophobic, so it's very good for brief analysis, for example. So water is repelling, and these types of materials, they can survive up to 400 degrees. So this is very important for sensor. So it retains properties. And this way, how to cover this complex morphology, you can see here, it's not so easy to cover everything. We cannot put just a drop of polymers on top, and to obtain sensors, it will not work because we have some penetration depth, gases, and volatile compounds. So that's why it's important to have a good technique to cover nanometer range and complete uniform these types of materials. So that's why it's implemented a new technology, it's ICBT, where I used these types of micro heaters, hot filaments, monomer A, monomer B, initiator, and on surface can be deposited any types of polymers. in a very simple way. So it's CVD, we know, chemical vapor deposition, and this one, ICVD, this is initiated chemical vapor deposition of polymers of different types on surface of our oxides, creating polymers or copolymer materials. So in this way, this type of new technology, which not so many reported, you can search in literature, you will not find results, only few of our papers. We just started these directions. The technology was proposed by Professor Thomson from USA, from MIT, with highly developed university. And Professor Faufel, they met at some conferences, and they transferred technology to Kiel University. So now Stefan is working, and Lynn, we are working together on a series of works. Professor Faufel, he was here also at previous conference, reported in plenary, but now he retired this year, and Professor Ameri takes the lead. What types of polymers can be deposited? Really a lot of different types of polymers. I will not stop here, but many types can be. Our PhD students, they try to do analysis of literature, and most important is that we can control. We found a good thickness for these materials. Theoretical analysis was done, reported in our works, how to demonstrate that this polymer are high quality, and it's exactly what we want. It's done different measurements, so it's demonstrating that exists this ring structure between silicon and oxygen only. By covering different types of oxides, we can study and analyze these materials. How can be fabricated different rings, type dimensions, and KH ring, and so on, by this approach. Also theoretical studies are done. Also we are very interested in study how this electropotential map, what's happening inside between these rings. It will allow to pass gas to the sensors, and which one will pass, which one will not. So this is in our investigations. Like I explained in one of our previous work, idea came to develop copolymer. So what will happen if we use different types of polymers at the same time? So we made already sensors and reported on our works. Short about structure, Professor Fomin asked of the device. It's something like this: a cell. Here we have monomer A, monomer B, initiator, and on top we have this filament. And by controlling pressure of these materials and controlling the temperature of this filament can be deposited in a really simple way, and it can be deposited, for example, the complete disk and so on, any surface. So technologies can be very easy transferred to industry, and they already created a startup company, so we'll start to sell these types of setups. Not technology. Technology we are studying how can be used these materials. So here shortly, without polymer, for example, we have one type of gas sensing. By coverage with polymer, we complete detection to completely a different gas, only hydrogen. Hydrogen is smaller molecule and it can pass through these rings, and it's one short application. And another approach is by using different types of porous crystalline materials. So we have to use high interaction sites, molecular sieving effects, so also not polymers in this case, but I use metal organic frameworks to tune selectivity of these materials. And here we have, I will not stop due to time, but we can see that sensors are working really good in these materials. Also study the theoretical, and main highlights are industrial, environmental, medical field of applications of TAP, but of course market is not stopping, it's still growing up. So we have to catch some spots for our research to develop something new, and that's why you saw on the news 2 days ago Nobel Prize for Chemistry. It was given for metal organic frameworks. Here, Technical University of Moldova, we already studied for the last few years this metallic organic frameworks and a Horizon project. between 10 different universities in the European Union, and our PhD student is doing research on these types of materials already, not developing but implementing sensor applications like SIP. So this is Nobel Prize for Chemistry this year, obtained by 3 professors from Japan, Austria, USA, and most important, we have here professors from Japan, and one of our PhD students in this project also is from Japan. So he is working on growing these types of materials, then we implement. So why it was given this Nobel Prize in Chemistry for this metal organic framework is because it has an enormous potential, and we are still developing it. So what we did before it was announcing this, we just used many types of very simple substrates covering with oxides biotechnology or process technology, creating contacts. From another side, these metal organic networks are dispersed, covered on surface, and obtained new types of hybrid sensors and devices. So, for example, here we have morphology of non-covered material grown here at our department, and by coverage with this metal organic networks and detailed analysis. We did everything from structural analysis, chemical, and theoretical part also. And just a few days ago, before announcing this Nobel Prize, we got accepted in 2 journals. One of them is Material Chemistry Frontiers with Rajat paper. For his PhD student also were involved some of our PhD students from Department of Microelectronics. I will not stop on details, but we can see that these types of hybrid sensors, they are working, they are stable, and it was investigated also in time. For example, after 4 weeks, they are still functional, operating, and high humidity, what we need for brief analysis, for example, they are still working quite good, can distinguish between different concentrations of gases. So what was planned in these types of new materials, we already have one application for them. Of course, we are trying to explain all theoretical part of this to develop, and in every paper we are adding these chapters or paragraphs about mechanism, about physics, applied physics, for all this, so people can do it better and develop new materials. And like always, people asking about comparison, and in every paper we are doing comparison of what was published before us and what we did, and we found strong points of our research. So it can be also in our works. Okay, what types of zeolites or metal organic frameworks are developed? Just being in one of our presentation 2 days ago, Professor Radilund was called from Germany, from TV, to give an interview about Nobel Prizes, because we are working in this field together. And what is more important, that we patented this already in Germany, and now is transferred to USA. Also patent on new types of materials. Theoretical part, I will not stop here. So we are always trying to use physics. That's why students have to study physics, solid state physics, and so on. It's very important to try to explain this, to make correct and good steps. So here are still some works to be published. Our students are working on this, explaining mechanism and so on. We don't have time to stop on this, but all these parts are in progress. Also chemical reactions on top and so on. So in conclusions, we can say that we can create nanosensors. Here we have nanosensors which we published 2 years ago about this nanomaterial, single nanowire covered with this metal organic framework. Then it was first taken in the European Union for a patent. It's filled already, several companies already wants it, and we just fill it another USA patent on this about nanosensors. Here outdoors, also we can see our PhD students here involved. Since it was also Nobel Prize in Moldova, Professor from Japan. He was working on blue leads, so I also worked on this in 2009 during my habilitation, and we developed really simple heterostructure made on nanowires, which is innovatively, and it was published in Advanced Materials. They are also working, so we are also on this way. Our students, some of them are here, they are studying this light emitting diodes. So it's also on trend, so they work really fast. And with Professor Tiginyanu also we published a series of papers about these types of devices. And much simple technology, just chemical deposition of nanowires on P gallium, and we can see blue leads, they are working really good, and reported in several papers why they are good. I'm also teaching already this material published to our students at master course. So we would like to say thank you to this Horizon project at Technical University. It's between 10 different universities and the European Union, and Moldova is in. And all of these PhD students from every university were here in Moldova, and they really enjoyed our university, and the Republic of Moldova is the Technical University. And of course, thank you to they were sometimes PhD students, now they are already PhD and still studying, working in the laboratory. Like I mentioned, Professor Adelon, this is only one group, so you have to understand, one professor and 25 PhD students working on this, and from time to time I'm also here somewhere. And Professor Amelot from Belgium, involving here mainly in chemistry, and about ICBD, this Professor Faulkner's team, it's here. All people have their input to this research. Thank you very much.
Thank you. Okay. Let's start with Professor Pomini.
Thank you, Professor Lupin, for very touching results of many years. Allow me to express one concern. I read very carefully press release of the Nobel Committee, and I have carefully followed your talks and your colleagues' talks on this fascinating topic. And I found many effects which were observed, documented, reported, but I did not find one effect. These frameworks, like your materials, they can not only absorb gases or some other chemicals, but they can also release them. I am sure that under certain, under specific conditions, they can be considered as very efficient accumulators of these gases or other chemicals. And if we speak about poisoning gases, then this is a new way to extremely dangerous chemical weapons. So my question is to you and to Professor Vasile: how can society somehow guarantee the future from this new danger, which might be as dangerous as artificial intelligence or some other new invention? So I am really very much concerned about this. Thank you.
Thank you very much, Professor. It's a highly important topic. I was a few years ago in the USA, we also working on this, catching all dangerous gases by using highly porous materials. So we worked on this zeolite, so they are metal organic frameworks, they are highly porous, so they can catch all this material. But it's really good question, but such dangerous gases can be catched and can be released somewhere. So this is again a huge point in security to be taken into account, like others, like you mentioned. But our goal in our research is to study how these gases can penetrate it, how to create this sensing effect and to implement. But of course, during all of these studies, we will find some answers to your question, how to identify, maybe by these sensors, we can tell, okay, this person, he has such type of material in his luggage, and he tried to take it from one country to another country to make some really bad things. So this is one of possibilities.
We are good guys.
We are good, but...
Okay. Okay, next one.
Thank you very much.
After me.
Thank you. Yeah, thank you very much for your very informative talk. I have one practical question. How stable this polymer covered layer is stable against degradation?
So we studied this question. So it is somewhere here. We can see it. If it's not uncovered material, 200 at 200, 250, it's still safe. After 400, around 500 already starts to degrade this polymer. Destroyed. Yeah. It's changing structure and degrade. So usually we are working in temperatures below this. So of course the goal is to make room temperature sensors. If they are selective to certain gas, because of these rings, because rings will not allow to flow large molecules of volatile compounds and so on. Sizes of these rings, they also can be changed by adding a new silicon and oxygen pair here. So ring can be changed for one gas, for another types of gas. But they are still surviving for this type of applications.
Thank you.
Thank you.
Last question, not last, one of the questions. In most cases, you showed that you're essentially detecting hydrogen. These are hydrogen-based sensor. Can you comment on the specificity or selectivity? Because you may have different environment you showed acetone. So you may have a different environment. So again, my question is on the selectivity and specificity of these sensors.
For these new types of materials, for example, for this metal organic frameworks, Nobel Prize. So we implemented it a few years. So I spent really a lot of time in clean rooms to fabricate these nanosensors, single wire, from zinc oxide tetrapods, like Professor Radilov showed, covered by Professor Stock. He is in Kiel. He is working really on, he developed a lot of types of this metal organic. And as we can see here, we have detection only to hydrogen. So no one gas can penetrate this framework. But if we change thickness and if we change type of this frame, this is ZF8, is one type of this ring of porous material. But if it's changed another one, then they can allow another types of molecules. So we are trying to find and to control this tuning for these sensors. Thank you.
Okay.
To answer your question about reuse technology.
Oh yes.
Again, as the technology continues to increase, we will continue to have reuse technology. So we have to put guardrails no matter what technology we use.
Okay, thank you.
Yes, sir.
Okay, let's give the certificate to the Professor Lupan. Okay.
Thank you.
The next is given by Ernesto Iadanza. That was great. Yes, from Italy. Okay.
Thank you so much for this kind invitation, in particular to Professor Sontea, who's not here, but he's a very good friend. And thank you for giving me the occasion for being, for the first time in my life, in your beautiful country. So we'll talk about artificial intelligence for evidence-based management of medical devices. So first of all, a few words about my university. I work for the University of Siena. I'm the director of the bioengineering lab, and it's a very vibrant environment. We have students from all over the world. 90% of my students are not from Italy. All our courses are taught in English, so it's a very interesting place. And in particular, we have some research topics, most of them related to AI. So the application of artificial intelligence to clinical engineering, or if you prefer, health technology management. So how to manage the actual technology we are using in our hospitals, and also AI for health, so clinical decision support systems. In particular, we are focusing now on using AI for analyzing the relationship between microbiome, human microbiome, and different pathologies, and also from the environmental point of view. Health technology assessment, evidence-based maintenance will be one of the things I will point out today. And of course, also there's a lot about the medical device regulation, because in Europe, as you know, we have this regulation for medical devices, which is very strict, so it is a huge burden both for the notified bodies, so for the regulatory bodies, as well as for the manufacturers, of course, but also for scientists. So a couple of words about the IFMBE, so the International Federation for Medical and Biological Engineering, which is, by the way, co-sponsoring this conference. It is a federation of societies, so not of people directly. You cannot be part of it through either than through your national society, and it has now 67 years. So it's by the way the only international federation which is not for profit. Okay, so it is the house for the biomedical engineers worldwide. This is how it is structured. So we are part of, if I manage to find the laser pointer, otherwise I can do without it. So we are part of the United Nations through the UNESCO and the International Science Council. And then there's an umbrella federation, this IUPESM, which is basically a way to be part of UNESCO, together with our sister society, which is IOMP, so medical physicists. Okay, and we have our global conference every 3 years. The last one just finished a few days ago. I'm flying all the way from Australia here to Moldova, because that's where it was, and the next one will be in 2028 in Mexico. We are in official relationship with the World Health Organization, which is a large part of the activities we run in the Federation. This is now the map of the member societies. Moldova, of course, is part of it. And as you can see, there are still some great parts. We are working on it. In particular, we are working a lot with Africa. It used to be only South Africa a few years ago. Now, this is not updated because coming from Australia, we have 8 new members coming in. We are like 83 societies from all over the world, plus a few transnational members like the American College of Clinical Engineering, or the IAMBES, the European Association for Engineering, or IEEE EMBS, I'm sure you are familiar with. So it's the biomedical societies inside IEEE. In this structure we have a council of societies, so all the IFMBE member societies, the 83 societies I did mention, are together in this council of societies. I am chairing the council of societies together with the past chair, the president, and the secretary general as ex officio members, and the 5 regional group representatives. Some of those faces should be updated because we just had elections. I didn't have the pictures, so I couldn't update it, but it will be my duty to do it as soon as possible. We have elections every 6 years, so we had to structure the federation in regions, no? Because, for example, up to 2022 conference in Singapore, Europe and Africa, they were together, no? And now we have a region for Africa, and we are trying our best to do the so-called capacity empowering. I don't like capacity building because there's no need to build anything, it's already there. What you need is to empower these people and their capacities. And we can do this also through the e-learning platform. This is relatively new, a few years now. go and take a look if you want. It's completely free, it's open for everyone. And it is the joint effort between the three, say, operational branches of the Federation, which are the Clinical Engineering Division, the Health Technology Assessment Division, and the brand new Digital Health Division. We had to add, of course, a Digital Health Division nowadays because it's becoming more and more important. Thanks to this collaboration, I was lucky enough to finalize the Clinical Engineering Handbook a few years ago, which was a combined effort of 110 co-authors from all over the world, touching more or less all the most important parts of clinical engineering. So in the first edition, which dates back to 2004, so not 50 years ago, but there was no IT, for example, there was no human factors, there was no health technology assessment. This is a profession which is very rapidly changing, so there is the need to try and cope with it. So, coming to the topic, evidence-based maintenance. Of course, EBM really sounds like evidence-based medicine. So our idea is, why don't we try and base our maintenance of the equipment based on evidence? It's not that easy, because what is evidence? We should define what is evidence, and then once we decide what evidence is, how can we extract evidence? Because most of the sources of this evidence are not machine readable, are human readable, are made for humans. So we need a few techniques to try and cope with it. We started in 2019 with this first experience in Florence. This is the hospital of Careggi, which is the largest hospital in Tuscany and Florence. And we tried to apply this methodology on an actual, on an actual case. So we're talking about more than 16,000 pieces of equipment, so it's quite a large hospital serving not just Tuscany, but people from all over Italy is coming there. So what do we want to measure? So first of all, we are trying to propose some KPIs, so some key performance indicators, to try and understand, first of all, how the performance of that clinical engineering department is, and then how it's running over time, but also benchmarking with other departments, maybe with other hospitals or other countries. You'll see this is not that easy to do, but this is what I'm not going into each and every one of them, of course, but if you're interested, there's a publication for that. So each KPI is, for example, the downtime, so the non-availability time, or the MTTR, so the mean time to restoration, or the mean time between failures, and so forth. So we have some operational, but also financial indicators trying to understand how, for example, the scheduled maintenance cost is with respect to the total maintenance cost. And this has changed over time. One of the most important things the clinical engineering department was called to do was maintenance. Nowadays, most of the maintenance is outsourced. So it is the same KPI, should be read in a very different way in the last few years. And then, once you analyze the maintenance reports, you want to know what went wrong. To understand in different, for example, departments, if there is a problem of use, maybe you need to train more that department, or maybe there might be a problem related to people working there. Maybe there's a lot turnaround of people, so you have new untrained nurses, for example, or maybe you have different situations between hospital and hospital. I was in Ottawa in Canada, and there was a hospital where all the equipment, whatever the equipment, from surgery to infusion pumps, were coming from the same manufacturer. This is impossible in Italy, by law. In two different departments, you're going to have like 20 different manufacturers. So the actual context might be very, very different. So we wanted to be able to classify these faults, and we provided a standard classification, and I just realized this has been used in more than one country. So we start to have comparisons thanks to this kind of standardization and normalization. So this is one of the things you could try and analyze. So you go deep into, for example, electrosurgery units, and you realize that batteries are typically the problem, but, I'm talking about defibrillators, are the problem, but there is no much added value in the scheduled maintenance. You check the battery, it's okay, it's like your car. And tomorrow morning you go and try to turn on your car, and it doesn't work because the battery goes down in a second without anything to do with that. So maybe you should change your protocol. There are standards and there are indications from manufacturers, but this is open loop. We are, at least I'm an electronic engineer as a background, so I hate open loops. I like negative interaction. So we want to be able to measure what was the outcome of actually putting in place that particular protocol. We followed up a few years later in Pisa, still in Tuscany, still a large hospital, the second largest hospital in Tuscany. In this case, we focused more on diagnostics, so large equipment like CT scans, MRIs, DRs, and so forth. And again, we had to refine and expand the initial failure code classification because we realized there were, for example, something to do with environmental causes like construction yards or cleaning services or even flooding. Typically, the maintenance in a hospital, you know where it is? Underground. That's the worst idea ever. So having it in the basement, the source of maintenance means that after a flood, your whole hospital will be without maintenance in the moment it is more needed. So this kind of also causes needed to be taken into account. And then, okay, so more details. So if you're interested in knowing more about evidence-based maintenance, you could refer to Vincent Wang, who's been the first one talking about evidence-based maintenance, and he is still very active in this field. Now, I said it's not easy to expand this to all over the world, to the whole world. Why? Because there is no standardization. So let's start by the nomenclature, the way we call things. So an ultrasound machine is an ultrasound machine. But if you call it echographer, and I call it US machine, and so forth, there's no way I could reconcile different databases now. Basically, a query would not be that easy. So there are nomenclatures, but, and this is a Scopus review we published, and which has been captured by this WHO publication. So as you can see, there are nationally developed nomenclatures. There are 45% of countries who have no official nomenclature at all, and then there are some which are the European, the global, the UMDNS, so the universal, of course, because we have the European medical device nomenclature, and then the British had the global medical device nomenclature. So the American had to do the universal medical device nomenclature, of course, but it's not universal at all. As you can see, it's just 9% of the people using it now. So in 2021, September, I was giving an advice to the WHO Assembly, the Member States' second information session on medical devices nomenclature. So on that specific topic, trying to raise this concern and to obtain a statement and possibly a resolution to overcome this problem. So a few years later, we are now in 2024, March, WHO adopted only two nomenclatures, the European medical device nomenclature and the global medical device nomenclature. So we are getting closer to have the same, say, language, the same standard all over the world, but still, it's in progress. This is a very recent, we're talking about March 2025, initiative by WHO, and we as IFMBE are part of it as an NGO, which is the Global Diagnostics Coalition. So again, trying to have a global approach is the key, where you can contribute also as members of this federation. And then we said, okay, let's try and analyze these reports by using AI, by using natural language processing in particular. Why? Because as I said, all these reports, they are just written in plain text. Also, you want to extract evidence by taking advantage of recent technologies like NLP. This was the PhD of Alessio Luschi, a collaborator of mine in my lab. And you can see from these numbers how the health information related failures, these are data coming from the FDA manufacturer and user mode. Anyways, it is a database of adverse events reports. Okay, so you can see how in the last years it is ridiculous how it came up. And of course, because we have so much software in our devices. And what's more interesting is that now we have software as a medical device. So software per se is now, or can be, a medical device. So while we might know more or less what are the failures in an ECG, it might be the electrodes, or it might be the battery, it might be the network connection, but what are the failures in a software, it's way more complicated to find out. So we're trying to do the same thing. So based on this data, and as I said, we started with mode because in FDA they have been doing this for a long time, for a really long time. So there's a lot of reports, a lot of data. We start to have something similar in Europe, but still in its infancy. So we analyzed those texts, and we did this by applying the so-called explainable AI. So we want to know why the classification was falling in one category or another, because there might be a mistake. Now, having a supervised approach is not trivial because you need labels, and who is giving you these labels? So we were lucky enough to have a small amount of maintenance reports labeled by colleagues in Australia, and so we used it for the supervised approach, and these are a few results. I don't think we have time to go into it, but it's the typical SHEP approach to understand what it could be. So we have new failure codes, and we are trying to also incorporate standards by AMI, for example, which is the American Medical Devices Association, in our classification. Now, there is no universal fault taxonomy yet. This is still work in progress, what we are trying to do. And this is the last thing we are doing now. It's a work in progress. So you start with the data preparation, and then you extract tokens, and you sample you select the samples, you label them, and you fine-tune the model. Well, this is quite a typical AI approach. But that labeling is the tough part. So what we try to use now is the so-called self-supervised approach. So basically what you do, you have a sentence, a maintenance report, and finally let's use an LLM to say, to complete the sentence. No? So the problem was related or was due to, and the word that will come out will be one of the possible classes. This is what we are now doing. So to extract tokens, and here you go. You have categories like induced by service, software, driver, cybersecurity, data quality, network, again, human factors, design and manufacturing. There's a lot which is similar to the hardware devices. Okay, so few results. Let me just skip. This might be too technical. It's a BERT model, so it's a transformer by Google. I think it's quite well known. This is what we used, and we started obtaining some encouraging results, not so good to be honest, but it's a very complex and multi-class problem, so you're not aiming at 99% accuracy, of course, otherwise it would definitely be overfitting. So these are the results so far. As I said, this is not yet published. We have a paper under review, but it's brand new what we are trying to do here. And to conclude, September 2026 in Siena there will be the Mediterranean Conference of IFMBE, so you are more than invited to come and to contribute. It is the IFMBE conference that we do every 3 years. It's coming back to Italy after 22 years, so there's a lot to do from now to September. and we secured this beautiful venue. It will be all for us, so there will be also room for parallel sessions and discussions and nice sightseeing. This is a local organizing committee, as you can see, in perfect balance between men and women, so gender balance is okay so far. And we wanted it to be in the heart of the city, so it's in the exact center of Siena, which, as you know, it's a beautiful venue. And this night at 4, someone from Australia didn't realize it was 4 a.m. and told me that Siena is now the green leaf for sustainability. So this will be for sure also one more occasion to see the beautiful countryside. And that's it. Thank you. That's my email.
Are there any questions?
Yes.
I have one. The input data, how large is it? And I saw there that manually you will extract or you will eliminate the wrong information from this data.
Yeah, you're raising a very good point. So basically the data quality. So the input are maintenance reports, which are very variable because it might be a very straight sentence, not a report, it's just battery broken, or maybe you have a long description of what happened. And sometimes you have to go back to the technician if you have access to him to have a better description. So it is plain text. And of course there are some stop words and this kind of stuff, but also when it comes to quality there are some nice things, like for example you have a report, if you start with the FDA reports, you have reports from patients. There's a nice one saying that there is a dog in this dental clinic which is leaking everywhere, and which took the quality of that is of course not comparable to a report from the manufacturer, Siemens telling you that it was that component. So definitely it needs a human in the loop, of course, yes. Even before feeding the system, otherwise, as you know, garbage in and garbage out. This is what we're dealing with.
Yes, thank you.
Thank you.
Some other questions? Yes, please.
So, thank you for your presentation. And my question is, for example, to register medical devices, this is interesting entertainment for companies. You have to a lot of improvements, electrical, medical, blah blah blah. But in this case, for software, because artificial intelligence is software, what is the situation nowadays? Because we have not just the software, but also decision factor, like artificial intelligence, and how it works, let's say, like how it works, and what the situation today with this one.
Thank you. That's a very complex topic we're raising now. So it's very scattered, the situation. So I'm involved with a few organisms or regulation and also notified bodies which are trying to cope with software. So let's say this kind of approach can be very helpful both in the so-called post-market surveillance, to see what happened once, as you know, at least in Europe, you as manufacturer are responsible for that device for the whole life cycle of the device. So that would be very useful to analyze in a semi-automated way the flow of information coming from the market as a feedback. But it could also be, and it should be, part of the design. If you want to have a risk-based design, this could be very good to analyzing and to predict what the possible risk would be with your software. When it comes to AI, as you know, we have a problem with, at least in Europe, with the fact that AI could be changing, could learn, which is the nice thing of AI. But if I'm the manufacturer and I'm signing a declaration of conformity, or I'm a notified body and I'm signing a declaration of conformity, I say this is definitely what, in terms of performance and risks, what is acceptable. But if the device is changing because it's trained, we have a problem there, no? And it's a regulatory problem. So at this moment, we are kind of using just 1 hour, no? Because we stopped the training, and we know it could improve a lot the performance, but we don't know in what direction. So this is something that in Brussels are trying to solve. So how with artificial intelligence based software as a medical device, we could actually monitor what's going on in terms of performance during the continuous training, by learning. Very complex topic, but thank you for your question, very good.
Okay, thank you. Next one. Still have the time.
Yeah, I would also like to thank you for your presentation. And my question is how does this framework, how is it used in practice? So I understand that you collect all of these reports, then you can extract the information on, let's say you have a medical device or software as a medical device, then you can say, okay, in this institution, this particular device is failing due to, let's say, XYZ. And from there, what do you do? Like you can, based on this information, do you suggest an immediate course of action, or do you use some kind of a predictive modeling to say where, like this institution will be in a certain amount of time? So how is it used?
Yeah, it can use it both ways. It can use it both ways. For example, to allocate your budget. To know that if you have a problem, let's give you an example. You have a problem with the operating system. You realize that most of the problems you are having are related to the changing operational systems you have, Windows or whatever it is now. So that means you should start programming a large investment, or maybe that you should do something to prevent this from happening. On the other side, if you use it on a day-by-day basis, you could try and understand that in this department, or maybe with that software as opposed to another software, you have a usability problem. So maybe you can report this to the manufacturer, because usability is part of the design process. But again, what you do for usability tests is corrected. So maybe in an actual use, you will find that there were many more problems than the ones you knew. And if I'm the manufacturer, but I'm not in touch with the end user, how could I know it? So this means trying to close the loop by having information from the ground in your specific setting, which might be very different from a different setting.
So essentially, this is a tool to produce some kind of a feedback loop, which can then improve your own, let's say, processes.
Go back to evidence-based maintenance. So this is a tool to extract evidence, and then the decision will come after.
Okay. Thank you.
Thank you.
Any questions, please?
Hi, Professor. So I'm just thinking on a practical point of view. Since it's a medical device, the investments, the amount, the cost of it is quite high. So let's talk about different countries, developing, poor countries and everything. Practically speaking, who is able to afford it? Or the capacity of the hospitals? Like for example, primary setting hospital or a tertiary setting hospital. Which kind of hospitals are more, capable of affording it? And different sectors of hospitals which is like more suitable for this kind of devices?
Yeah, very good question. So instead of developing countries, I like to talk about low middle income settings, because maybe in an advanced country there might be a specific setting when you have that problem. So definitely we have that in mind, and we have collaborations. Now there's a new project just started with Africa, with 32 different countries. And what we are trying to do is exactly what I said before. So to enhance the capacity that are already there. Typically, these are not the most expensive tools on Earth. Ideally, AI, when you have access to it, is not that expensive to realize. The most, let's say, expensive part is to have, how can I say, to have a good network, for having this information flowing. Because if I had to rely only on my specific data, that might be almost impossible. So in that article, we proposed an XML protocol for receiving maintenance reports from different manufacturers. So now we have in a large hospital in northern Italy, we have together GE, Siemens and Dräger, which are sending the reports according to that standard protocol. So that means that you start building a body of evidence. And another thing we are doing as IFMBE, those two divisions, the clinical engineering division and the digital health division, are for free, of course, because it's just voluntary work, trying to create a body of evidence with the help of WHO. So trying to collect maintenance reports from all over the world, making them interoperable, which is definitely not trivial, and creating a free source of information for all settings.
So this technology can be used with respect to, let's say, like as you mentioned about defibrillators and faults, to analyze them in a hospital setting, as well as in the patient information also, right?
Correct.
So when you're talking about the fault inside a hospital, there's a possibility of these data breach and confidentiality, and if such data is being released, it creates a sense of chaos among the public population. So how can these things be managed?
That's very important. That's a very important one. Well, in some countries it is mandatory to report adverse events to your ministry or to FDA, like in the case of the United States and so forth. And of course, from one side you want to hide it from the patients, from the other side you need to make this data available. So it's as always is a risk benefit. So we have to prove that the benefits are higher than the risks. And that's related also to the brains, the artificial brains you were showing me before. It's true that knife could be, or hammer could be used in a way or another. That's true. On the other side, we are creating an artificial user of a possible knife, which is a bit more high. So in this case, again, we have a problem of, if you want, kind of confidentiality, because this is also in a single hospital. Two departments are not always keen to let you know what their performance are, to change the information. And that's why, starting from the global perspective of WHO is very important. Because once WHO requires those data, those information, it becomes mandatory for the ministries of health, and this means also for the regions and the single hospitals to provide those data. And then you will need the technology to be able to assert it.
Okay, thank you so much.
Thank you.
Okay, thank you very much. That's for you. Okay, let's make a photo here. Yeah. Okay, thank you very much for a very nice talk. And okay, I have here some certificates of achievement. We had jury of young investigation competition, Professor Vladimir Fomin, Professor Liliana Vereshchuk, Professor Andrei Dragomir, Professor Gennady Kurochkin, and Professor Eduard Monait. This is a team which selected the best posters of our conference, and I invite here, Eduard, help me please, please come with me here. The first place in young investigation competition is Vladislav Genia. Okay, Vladislav, all the best to you. Here is a certificate, and here are some money. I don't know how much is it. Okay. The second place, it goes to Tatiana Malkova. Yeah, it's present. Okay, Tatiana. All the best to you. Yeah, and also we have for you also some money. And the third place
Fatima Mizamuden. Yes? All the best to you. This is the certificate. Okay, and here are some. Okay, and now it's time to close the conference. First of all, I would like to thank you, all of you, for nice presentations, for nice reports, and I hope you enjoyed. Even outside was raining, but you enjoy being in Moldova, you enjoy being at Technical University here in Chisinau, and I hope as a result of this conference, new projects will start. Some new bridges were done between our universities, and it was nice to report that almost people from 20 countries visited Moldova this time. We had many presentations, and my colleague Eduard Monaiko reported that almost all presentations were presented at this conference. And of course, I would like to mention the gratitude to my colleagues, Professor Sontea, Professor or Academician Tiginyanu, domnul Relian, vă rog, veniți încoace.
General.
Yeah. And my colleague Eduard Monaiko is here. Please come in, because also I want to say many thanks to students, graduate students, postgraduate students, which help us a lot doing this work. Also, thanks to the administration of Technical University, because they help with cars, with some other things. And in 2 years, please come again to the Republic of Moldova. We will wait for you, and also thank you for invitations to other conferences. I mentioned at the reception that Moldova chose our way to the European Union, and of course we will need your help just doing the law in the Republic of Moldova, having some partnership, and now we're applying to different organizations with projects, and our people will travel next couple of years to Europe with funding which is coming from Ministry of Education. Once again, thank you very much for everything you did to make very nice this conference. Thank you very much. Have a nice trip to your countries. And now let's make a photo here in front, all together. Yeah, please come in. Come the paper. Yes.